Have you ever thought that simply observing something might change what it is? Back in 1957, a physicist named Hugh Everett came up with a really interesting idea. He said that when we measure a particle, reality doesn't just settle into one outcome. Instead, every possible outcome occurs, each one in its own separate world. This idea, called the many worlds interpretation, is still one of the most talked about theories in physics. Some scientists are all for it, while others completely disagree. In 1957, Everett walked into his advisor's office at Princeton with an equation he said could change everything we know. He believed he'd cracked the mystery of quantum mechanics, but his findings scared him. At that time, everyone believed particles chose one state when observed. Everett showed that instead of collapsing, reality splits. His advisor, John Wheeler, almost didn't accept his thesis because it seemed too far-fetched. According to Everett's theory, every time a quantum event occurs, new universes spring up, not just in a metaphorical sense, but as actual separate realities branching off from ours. Wheeler worried about what this would do to Everett's reputation and advised him to calm the language down a bit. But Everett stuck to his findings because the math backed it up completely. When you observe an electron, you don't make it choose a location. You and the electron basically get linked together. One version of you sees the electron in one spot, and another sees it somewhere else. Both are real and carry on in different yet parallel worlds. This isn't just theory. It's what the equations honestly show when you follow them to their natural end. Everett's ideas were ignored for decades, while others came up with complex explanations for quantum behavior. They invented unseen waves, directing particles, or suggested consciousness had a special role. They made up extra rules for when and why things settle into a state. All these were additional complexities not needed for Everett's simpler explanation. Then, in the 1980s, David Deutsch at Oxford took interest in Everett's theory. Deutsch saw that if parallel worlds do exist, they could explain why quantum computers are so powerful. A quantum computer with 300 bits could handle more calculations at once than the total number of particles in the observable universe. Deutsch suggested that quantum computers might be using resources from these parallel universes to do their calculations. This renewed interest in Everett's idea because the math he used could be tested with experiments. Tests showed that particles act just like Everett said. When two particles interact, their connection remains no matter how far apart they are. If only one reality existed, this would seem impossible. But it makes sense if particles exist in multiple branching worlds at the same time. Now, places like Caltech, MIT, and Oxford are seriously considering Everett's many worlds interpretation as a top theory for how reality works. It explains quantum mechanics without needing extra mysteries or rules and matches experimental results that have puzzled scientists for a long time. What's most interesting is that it predicts something other theories don't. If a quantum computer smart enough to be conscious were made, it would recall existing in multiple states at once. Everett's discovery goes beyond just physics. If he's right, every time your brain makes a decision, you split off into different realities. Every choice creates new branches, and every second multiplies your existence into countless parallel worlds. The real challenge is whether we'll ever find direct evidence of these many worlds. Odd signals from the universe suggest maybe we've already seen it. Imagine a single electron heading towards a barrier with two openings. Classical physics would say it goes through either one opening or the other. But quantum physics shows us something much stranger. The electron actually goes through both openings at the same time. When it hits a screen on the other side, it creates a pattern of interference. Waves from both paths overlap, making areas of light and dark. This experiment has been done many times. The electron truly is in two spots simultaneously. Now, consider this on a larger scale. An electron is composed of quantum fields, and so is every atom in your body and every molecule in the air. Each particle is in a state of superposition until it interacts with something else. When that happens, something amazing occurs. The wave functions don't collapse but merge. When two particles touch, their individual descriptions become one combined description. This is known as entanglement in physics. Once particles are entangled, you can't discuss particle A without mentioning particle B. They're part of a single system, even if they're millions of miles apart. Measure particle A, and you instantly gain information about particle B. Einstein called this spooky action at a distance and thought it showed that quantum mechanics was incomplete. However, he was mistaken. Entanglement has been verified in labs all over the world. Here's what's particularly fascinating. Every time particles become entangled, a new branch of the universal wave function is created. One branch shows the result, where particle A spins up, while another shows it spinning down. Both branches are equally real, evolving by the same laws of physics. You just can't notice the other branch because you're entangled with particle A in a specific way. Think about how often particles interact. Photons from your screen hit electrons in your eyes. Those electrons set off chemical reactions in your optic nerve, and signals travel through your brain's neurons. Trillions of quantum interactions take place at each step, with each one causing more particle entanglement and splitting reality. The splitting is endless. Right now, for instance, cosmic rays from distant supernovae are colliding with molecules in Earth's atmosphere. Each collision creates new branches. Radioactive atoms below your feet decay randomly, creating parallel worlds where the decay happened at various times or in different directions. The universe branches trillions of times each second just on Earth. Multiply this by every star, planet, and galaxy in the observable universe, and the rate of splitting becomes mind-boggling. David Deutsch estimates that even simple quantum systems generate more branches than there are atoms in the observable universe. You might wonder where all these universes are. The answer lies in the nature of quantum reality. They don't exist somewhere else in three-dimensional space. They exist in quantum configuration space, a place with many more dimensions than the three we know. Every branch is in the same physical location as us. They overlap exactly, but remain causally separate, except during rare moments when interference happens between worlds. These moments could explain things we can't otherwise figure out. In 2004, NASA's Wilkinson Microwave Anisotropy Probe mapped the oldest light in the universe. The cosmic microwave background is visible from every direction, a relic from when the universe was 380,000 years old. Temperature differences in this ancient light show how matter came together to eventually form galaxies. Most of the map appears smooth with small variations. Then astronomers saw something was off in the southern sky. A region about 5 degrees wide, roughly 10 times the size of a full moon as seen from Earth, was way colder than the areas around it. Not just a little colder. This area measured 70 microkelvin below the average temperature, and in some parts, it dropped to 140 microkelvin below. Other spots in the cosmic microwave background only vary by about 18 microkelvin. This is known as the cold spot. According to standard cosmology, fluctuations that large should only show up in areas 1 degree wide, not 5 degrees. There's about a 1 to 2% chance of such a big cold area forming by chance. So it's technically possible, but unlikely enough that it needs an explanation. People first thought maybe a supervoid was to blame. Maybe there's a huge empty space between us and the cosmic microwave background with fewer galaxies than usual. Light going through this emptiness would lose energy and look cooler by the time it reached our telescopes. In 2015, scientists thought they found evidence for this Eridanus supervoid, which would be 500 million to 1 billion light-years across. If true, it would be one of the largest structures we know about. But when Durham University did a closer survey, they used the Anglo-Australian telescope to map galaxies around the cold spot. They compared this with data from the Gamma survey, which had logged galaxies elsewhere. Their results, published in 2017, completely disagreed with the supervoid idea. The galaxies around the cold spot seemed normal. There was no giant void. The Durham team reached a worrying conclusion. If no supervoid was causing the cold spot, then something from the early universe must have actually made a genuinely cold area. But what could it be? The Big Bang models we have can't explain cold areas this large. Temperature changes should even out over such big distances. Something didn't follow the expected rules. One bold idea stands out. Cosmologist Laura Massini-Houghton suggested the cold spot could be a mark from when our universe bumped into another one during the inflationary period. Right after the Big Bang, space expanded faster than light. If the eternal inflation theory is true, it created countless bubble universes. Some of these bubbles might have collided with ours before they were pushed apart for good. A collision would send energy waves through the universe, like a wake behind a boat, changing the temperature of the cosmic microwave background in a certain way. The cold spot's shape and temperature fit predictions for such a collision. Even though it's a slim chance, if other explanations don't work, the cold spot might be evidence that parallel universes aren't just theoretical. They could be connecting with us now. The cosmic microwave background holds information from the earliest moments of our universe. Once the universe cooled enough for atoms to form, light could travel through space freely. That light has been moving toward us for 13.8 billion years. So, we are seeing the universe as it looked in its early days, long before stars or galaxies formed. Think of the cosmic microwave background like a photo. Temperature differences in this photo show density changes in the original plasma. Denser areas became the spots where galaxy clusters eventually formed. Less dense areas became cosmic voids, revealing how our universe's structure started from something smooth. Scientists can predict this pattern, and our best cosmology models, honed over years of study, say temperature changes should follow specific rules. When we measure the actual cosmic microwave background, it lines up almost perfectly with these forecasts. Almost. The cold spot is the exception. Here's why it matters. If the cold spot came from regular quantum changes early on, we'd see similar odd spots elsewhere in the sky. Big cold areas should appear more frequently, but this one is unique and isolated, hinting at something unusual in that direction. Matthew Kleben, a physicist at NYU, modeled how a universe collision might look. When two bubble universes meet, they release energy at the boundary, sending it out as a spherical wave. Inside one of the bubbles, we'd see this as a circular pattern in the cosmic microwave background. The pattern's size depends on how far away and when the collision happened. Kleben's calculations forecast a cold spot with specific geometric traits. It should look roughly circular, with a certain temperature change from the center to the edge. The cold spot fits these predictions fairly well, not perfectly, but close enough to take seriously. The European Space Agency's Planck satellite, launched in 2009, gave even more detailed views of the cosmic microwave background. With 3 times the resolution of earlier missions, Planck could spot details previous telescopes missed. If the cold spot was just noise or a glitch, Planck would show it. Instead, Planck confirmed the cold spot and clarified its boundaries. Scientists analyzed Planck's data for signs of multiple universe collisions. Some theories suggest eternal inflation should lead to many such collisions, not just one. Early findings hinted at evidence for 4 separate collision marks. Later checks showed these signals were likely just random noise. No solid proof came out. The cold spot is still the strongest candidate. It's right at the edge of what regular cosmology can explain by chance alone. Some scientists say we shouldn't jump to exotic theories for a 1% chance event. Others argue that a 1% probability is worth exploring alternatives. Professor Tom Shanks from Durham University made the point clear. If further analysis rules out all regular reasons, then the cold spot might be our first sign that other universes exist. We need more ways to test this idea. Quantum mechanics shows particles don't have definite properties until something forces them to pick. An electron doesn't have a set position or momentum. It's a wave of probability spread out in space. Only when we measure it does it appear in one spot. This seems odd because nothing we see every day acts like that. A coffee cup on your desk is just there. It doesn't exist in multiple places at once. The key difference is size. Tiny things like electrons can stay in superposition. Big objects made of many particles lose this state almost immediately due to interactions with their environment. Physicists call this decoherence. The environment constantly measures big objects through endless tiny interactions, like air molecules bumping into them or photons bouncing off. When objects interact with their surroundings, it messes up quantum effects, though superposition is real. The double-slit experiment clearly shows this. If you send electrons through 2 slits one by one, each electron makes a dot on the screen. Over time, you see an interference pattern, showing that each electron goes through both slits at once. The superposition means the electron takes both paths until it hits the screen. But when we want to find out which slit the electron goes through by observing, things change. If we put detectors at each slit to see the path of the electron, the interference pattern disappears. The electron then goes through just one slit. Observing it changes the result. Conventional thinking is that observing causes superposition to collapse. The electron starts in different states, and measuring it makes it choose one. This leads to tough questions. What really counts as observing? Is consciousness needed for this? When exactly does this collapse happen? And why don't quantum equations mention a collapse? Everett's many worlds theory suggests something else. The electron doesn't collapse, you do. Before measuring which slit the electron uses, you're in superposition too. One version of you sees it at slit A, another at slit B. Both versions are real, but in different branches of reality. In each branch, you see the electron going through one slit because you got tangled up with it. This idea applies to everything, not just electrons. When light enters your eyes, photons interact with molecules in your retinas, change their shape, and send signals to nerves. Each step is part of a superposition. Every measurement you make ties you with the object you're measuring. You split into different versions, witnessing different outcomes. Everything in the universe is in superposition. All possible states of matter and energy exist together in the universal wave function. We only notice one version because we're part of this system and can't step out to see everything. We stay on one path while endless other paths unfold around us. If this sounds hard to believe, remember that scientists have directly measured quantum superposition in labs for particles, atoms, and even small molecules. The math checks out, and experiments confirm it. The debate is whether this applies to humans and whole universes. In 1926, Erwin Schrödinger came up with an equation describing how quantum systems change over time. This equation uses a wave function to show how things change from one moment to the next. For just one particle, its wave function shows where and how fast it can be. The equation doesn't talk about collapse or observation, just smooth change. What about several particles? Then the wave function becomes more detailed. Instead of showing one particle's place, it shows them all, capturing their connections. When particles interact and connect, the equation considers this automatically through the wave function. Here's a bold idea. Apply the Schrödinger equation to every particle in the universe to get a universal wave function that shows all matter and energy's state. This wave function changes predictably according to the equation. No randomness, no collapsing, and no special observation rules needed. Imagine one mathematical thing that changes smoothly over time based on known rules. This is what the many worlds interpretation is built on. The universal wave function represents reality itself. Everything that exists now, has existed before, or will exist later, is part of this mathematical structure. When we look at the universe, we're actually viewing a tiny fragment of the wave function. We're seeing just one of many branches. The other branches are just as real, but we can't directly see them. The wave function has a structure that's hard to imagine. It exists in a special kind of space, with 3 dimensions for every particle in the universe. Our universe has about 10 to the power of 80 particles. That means the space for our universe has 3 times 10 to the power of 80 dimensions. It's impossible to picture it. Even abstract math can't capture it fully. Yet, the wave function follows relatively simple rules. The Schrödinger equation explains how exactly the wave function changes. If you know the wave function right now, you can figure out what it was in the past and what it will be in the future. This process can be reversed. No information is ever lost. What happens in one branch is balanced by something in another branch. This brings up a big question. If the wave function holds all possible outcomes, is anything really happening? Is time just an illusion? Some scientists, like Sean Carroll, who supports the many worlds idea, believe time is real. Events still happen in order within each branch. The branching happens over time. We move along one path in the wave function. Others, like Julian Barber, think the wave function shows a reality without time. Every moment is there at once in this space. Our feeling that time passes is just how we experience the wave function. Past, present, and future are all real, spread out in a vast landscape of quantum possibilities. Either way, the universal wave function suggests something huge. Every possible history happens somewhere in the space of quantum outcomes. Your life has many branches, where you made different choices, went through different events, and became different people. They all unfold now in parallel existences. 2 particles meet in space. Their wave functions merge. At that moment, something significant happens. Before they met, you could explain each particle on its own. Particle A had its wave function. Particle B had its wave function. Simple and separate. Once they interact, they can't be separated anymore. Now, one combined wave function describes them both. This is called quantum entanglement. When entangled, the particles share a state even if they're separated by a galaxy. If you measure a property of particle A, you immediately know something about particle B. This connection seems to happen faster than light could travel. Einstein didn't like this and called it spooky action at a distance. He thought there had to be hidden things carrying information normally. In 1964, John Bell showed these hidden factors couldn't explain entanglement. He came up with inequalities that any hidden variable theory must follow. Experiments show those inequalities are broken. The particles really share information instantly. There's no signal passing because they aren't separate. It's all one system. In the many worlds view, entanglement is how new branches are created. When your brain deals with information, electrons in your neurons interact with each other. When electrons interact, they get tangled up. The wave function of the universe splits. One part has neurons in state A, and another part has them in state B. You split into different versions, each thinking differently. This branching happens all the time at every level. Around you, air molecules bump into each other about a billion times every second. Each bump tangles the molecules, and each tangle creates a new reality. Photons hit your eyes from your device at trillions per second, each causing a tangle and creating branches where you see slightly different light patterns. These branches grow fast. Starting with one universe, one tangle makes two branches, then four with another. After just 100 tangles, the branches outnumber atoms in the visible universe. After 1,000 tangles, the branches are beyond what we can easily express in normal terms. How many branches are there now? No one knows for sure. Quantum mechanics doesn't say if the number is finite or infinite. Some physicists think it must be infinite because of continuous variables, like position and momentum in the universe. Others say it could be huge but finite, if space and time have a basic level at the Planck scale. What we know is, the number is massive. David Deutsch said plainly, the number of parallel worlds is more than 5. It's more than 1 million. It's far bigger than what we can easily understand. And it keeps growing every microsecond as particles interact and tangle. Each branch is completely real, with people like you in them, all following the same physical rules. The branches can't talk to each other directly. Once they split, the branches stay separate and can't affect each other. Information can't move between them normally. However, some physicists now suggest that brief interference between nearby branches might happen. If this is true, it could change our understanding of how separate these parallel worlds are. For almost 100 years, physicists have debated what happens when you measure a quantum system. Before measurement, the system is in superposition. After measuring, you see one clear outcome. The wave function seems to collapse from many possibilities to one reality. This quick change doesn't fit with the Schrödinger equation, which predicts smooth, continuous evolution. So, when and how does this collapse happen? Niels Bohr, one of quantum mechanics' founders, said measurement is different from normal physical processes. Quantum systems follow one rule set. Measuring devices follow another. The divide between quantum and classical worlds is where collapse happens. This idea, called the Copenhagen interpretation, was dominant for years. The issue is, measuring devices are made of atoms, which follow quantum rules. So do the electrons in wires sending signals, and the neurons in your brain processing them. Where does the quantum world stop and the classical world start? Bohr didn't offer a clear answer and hinted that consciousness might be involved, which made many physicists uneasy with this mystical idea. Other theories tried to solve the problem differently. The pilot wave theory from Louis de Broglie and David Bohm suggests particles always have definite positions. They are guided by a real but unseen wave field. Measuring shows the position that was always there. This keeps definite outcomes but involves adding new ideas to physics. This makes the theory strangely non-local. If you change something here, hidden waves everywhere react instantly. The many worlds interpretation solves the measurement problem by denying any collapse happens. The wave function never narrows down from many options to just one. Instead, the observer is part of the system. Before you check an electron's position, you're also in a superposition. Your brain hasn't processed the measurement yet. After you look, one version of you sees the electron here, and another version sees it there. Both versions are real. This seems to add confusion rather than clarity. How can you be in multiple states? Why do you only experience one outcome? The answer is decoherence. Your brain has about 86 billion neurons, each packed with trillions of atoms. These atoms are always interacting with each other and the world around them. These interactions quickly create entanglement, isolating different versions of you from each other in microseconds. Once decoherence happens, the branches can't interact. They move independently. You in this branch can't access memories or experiences from other branches. They do exist, but you can't be aware of them because quantum interference has been dampened. Think about how this changes what observation is. Measurement doesn't collapse reality. It connects the observer with what's being measured. The universe doesn't care if the observer is conscious. Even a simple photodetector can cause branching, just like a human eye. Consciousness isn't needed for branching. It is just one type of system that entangles with others. This sorts out the measurement problem by showing there was never a problem. Quantum mechanics equations already explain everything, including observers and measurements. No extra rules are needed. Neurons in your brain fire through electrochemical processes that, in the end, rely on quantum events. An ion channel opens when certain molecules change shape. This shape change involves electrons moving between energy levels. Those electrons follow quantum rules. They are in superposition before the interaction happens. When the channel opens, the neuron fires. When it stays closed, the neuron doesn't. Both outcomes are real in different branches. This doesn't mean quantum physics mystically controls your thoughts. Classical physics explains most brain functions well enough. Neurons are big enough that decoherence happens really fast. Superposition doesn't last long enough to impact thinking or decision-making. Your decisions come from classical neuron activity, not quantum uncertainty. But here's what's vital for parallel universes. Even though quantum effects split quickly in warm, wet brains, branching still takes place. Each quantum event in every neuron splits reality. In one branch, a neuron fires. In another, it stays silent. These small differences usually don't matter much. Neurons fire or don't based on lots of inputs. A single quantum change rarely shifts the result. But sometimes, a quantum event happens at a key moment. A neuron is right on the edge of firing and just needs one more input. That input depends on whether a certain molecule is in state A or B. Quantum mechanics says the molecule is in both states at once. The universal wave function splits. In one branch, the neuron fires, and you think thought X. In another, the neuron stays silent, and you think thought Y. Imagine billions of neurons working nonstop to process information. As time flies, the paths where your thoughts could differ start to multiply. Most of these paths have you thinking more or less the same thoughts. Right now, you're reading this sentence and understanding it in most of these scenarios. But in some, something distracted you. In others, you might have misread a word. In rare cases, a small quantum change made your neurons fire differently, making you think about something else. Think about this happening throughout your whole life. Each moment, your brain has billions of little quantum events. Usually, these events create new paths that merge back quickly. All your versions of you end up thinking similarly again, thanks to how physics works. But sometimes, a quantum event happens at a major decision point. You pause before you speak. You rethink a choice. A memory pops up or stays hidden. These moments lead to paths that really separate. Over the years, these differences add up. You made different friends, chose different careers, live in various places. Each version thinks it's the only you. They all have memories going back to childhood and feel like the genuine you. From your point of view, in one of these paths, the others don't exist. Does this mean you lose your identity? Not entirely. The you reading this is a real person with true experiences. Your feeling of self isn't fake. It's just not the whole picture. You're part of a huge web of selves, each living its own reality in the quantum multiverse. Somewhere else, another version of you just read this and decided not to believe it. Back in 1935, Erwin Schrödinger came up with a thought experiment that challenged physics forever. He imagined putting a cat in a sealed box. There would be a radioactive atom with a 50% chance of decaying in an hour. If the atom decays, it triggers a device that releases poison. You close the box and wait. In quantum mechanics, the atom is both decayed and not decayed at the same time. This connects the poison device to the atom, and then the cat becomes linked to the poison state. Until you open the box, everything is in a mixed state. The cat is not alive or dead, but somehow both. Schrödinger used this to argue that quantum mechanics might be incomplete, since a cat can't be both alive and dead. But the math of quantum mechanics is solid, and experiments back up its predictions. The problem isn't in the science, but in how we understand it. We think that opening the box makes the cat either alive or dead. We believe one result is real and the other disappears. The many worlds idea suggests both outcomes exist. Opening the box doesn't change the cat's state. You and the cat become part of separate realities. In one world, you see a live cat, feel relief, and feed it. In another, you find a dead cat and feel sad as you handle the body. Both yous exist, and so do both cats, each living on in their own separate timeline. From your viewpoint in one timeline, it seems like the cat was always either alive or dead. Your memories make it seem like the result was set in stone. That's because your memories split too when you open the box. The version of you that saw a live cat remembers it living. The version that saw a dead one remembers it being dead. Later on, Schrödinger had another look at his thought experiment. In 1952, while giving a talk in Dublin, he suggested something surprising. He proposed that both outcomes of the experiment actually occur, but in separate realities that don't interact with each other. He admitted this idea might sound crazy, then argued it was the simplest interpretation of quantum equations. The cat experiment shows something important about measurements. The cat acts as a measuring device. When the radioactive atom decays or doesn't, the cat measures it by either dying or staying alive. The cat doesn't need to be conscious or smart to count as a measurement. Physical interaction is what really matters. As soon as the atom decays, it becomes linked to the mechanism that releases the poison. When the poison is released, it then links with the cat. This branching happens at each step. Consciousness doesn't play a role until you open the box, and you become part of the entangled system. You don't cause the branching. You just join in what's already happened. The cat was already in a state of being both alive and dead, fully realized in separate branches. You simply choose which one you experience. A brief moment after the Big Bang, something extraordinary took place. Space expanded at an incredibly fast rate. The universe doubled in size multiple times so that in less than a trillionth of a trillionth of a trillionth of a second, an area smaller than an atom grew to be larger than the observable universe today. This event, known as cosmic inflation, was proposed by Alan Guth in 1980 to address several problems with the Big Bang theory. Why does the universe appear smooth and uniform on a large scale? Why is space flat instead of curved? Inflation provides answers by rapidly expanding space, smoothing out irregularities and flattening curvature. The cosmic microwave background provides observations that support these predictions with great accuracy. However, Guth saw a consequence of inflation. Once it begins in a region, it may never completely stop everywhere. Quantum fluctuations create bubbles where inflation stops and regular expansion begins. Our universe is in one of these bubbles, but beyond it, space keeps inflating and producing more bubbles. Each bubble is its own universe with its own Big Bang, which is called eternal inflation. This process never ends globally, although it concludes locally inside bubbles. New universes are always forming, expanding, and filling with galaxies and stars. Some may have the same physical constants as ours, but others might have different values like gravity strength, electron charge, or quark mass. Many universes wouldn't allow for structure formation, lacking stars, planets, or complexity. A fortunate few, like ours, have the right conditions for interesting things to happen. Andre Linde at Stanford University improved this idea, showing that eternal inflation is not just possible, but almost certain, given our understanding of quantum fields. Even if inflation stops in most areas, quantum fluctuations will restart it somewhere else. The result is a vast multiverse of bubble universes, an outcome of our best theory about the universe's beginnings. Just how big is this multiverse? It's almost unimaginably large. Each bubble universe might be infinite in size, with potentially infinite numbers of them. Cosmologists consider this a level 1 multiverse, distinct from the quantum many-worlds multiverse. However, there could be a connection between the two. Some theories imply eternal inflation might differ across branches of the quantum wave function, with bubbles being separate due to continuously inflating space. Space expands faster than light. Once bubbles form, nothing can travel between them. These bubbles can't interact or communicate with each other. There's one exception. If two bubbles form close enough, they might bump into each other before they drift apart. This impact would leave marks on both. From inside one bubble, if you look at the cosmic microwave background, you might notice a circular pattern where the crash happened, like a bruise in the sky. This could be like the cold spot astronomers found. If that's a sign of a collision, it might be the first clue that eternal inflation creates multiple universes, meaning our universe touched another reality. Change gravity by a tiny fraction, and stars can't form. Make the electromagnetic force a bit stronger, and atomic nuclei fall apart. Adjust the electron's mass slightly, and chemistry doesn't work. These constants seem perfectly set up to allow galaxies, stars, planets, and life to exist. Scientists call this fine-tuning. It's intriguing because although these constants could have any value, they fall within narrow ranges that make structure possible. The odds seem incredibly low if they were random. Some people think this fine-tuning suggests design. If the universe seems made for life, maybe it was designed that way. This idea is the strongest form of the anthropic principle, which suggests the universe must have traits that allow for observers. Otherwise, there'd be no observers to notice. Scientists hesitate to accept this reasoning because it doesn't lead to further understanding. Saying the universe is fine-tuned for life doesn't explain why the constants have those values. It just repeats the observation. Most physicists look for real explanations for fine-tuning without suggesting purpose or intent. The multiverse offers such an explanation. If countless universes exist with different constants, some will naturally have the right ones by chance. We happen to live in one of those because we couldn't exist in any other. This apparent fine-tuning might just be a selection effect. We see a life-friendly universe not because it was designed for life, but because we can only exist in universes where life is possible. Consider a cosmic lottery, where each universe has random constants. Most tickets are losers, with universes that are too extreme for complexity. A small number are winners, creating universes where stars, planets, and eventually life can develop. We have a winning ticket, not because it's common, but because we wouldn't be here to check a losing ticket. The analogy breaks at a point because there's not a set number of universes. Eternal inflation could create limitless bubble universes, and infinite branches might exist under the quantum many-worlds theory. In an infinite multiverse, every combination of constants occurs infinitely, making fine-tuning not just likely but certain. Some physicists aren't fans of using the multiverse to explain fine-tuning, as they feel it undermines science's ability to predict. If anything can happen in the multiverse, then the theory loses its ability to explain things confidently. Some people say the idea of a multiverse comes from theories of inflation and quantum mechanics, not because we needed it to explain why our universe seems so perfect for life. We're just following the math, even when it leads to strange ideas. The debate isn't settled, but if the multiverse is real, then our universe isn't unique. The things that make life possible here are just random factors in a huge array of possible universes. Somewhere out there, other beings might be asking the same questions and having the same unsettling realizations about their existence. Roger Penrose is different from most physicists when it comes to the idea of parallel universes. He thinks the many worlds idea doesn't work because it ignores gravity. Quantum mechanics does a great job explaining particles and fields, but we still don't have a complete theory for quantum gravity. Penrose believes gravity is key to figuring out what's real and what's not. He focuses on how mass and quantum superposition relate to each other. Small particles like electrons have almost no gravitational pull, so they can stay in superposition indefinitely on their own. But large objects, which have significant gravitational fields, bend space-time around themselves. This is interesting because when an object is in two places at once, it creates two different gravitational pulls, leading to two different space-time bends. According to Penrose, this situation can't last. Gravity eventually causes the wave function to collapse, making one reality real and discarding the others. When an object's superposition creates significantly different space-time bends, gravity makes one version real and eliminates the others automatically. There's no need for observation or conscious measurement, just gravity acting. The point at which this happens depends on the object's mass and how long it can remain in superposition. An electron can stay in superposition forever, since its gravitational field is too tiny. A tiny particle might remain in superposition for only a second, while something as big as a cat resolves almost instantly. Bigger objects settle into a single reality faster. Because of this, large-scale splits don't really happen. Particles might split in different states, but those splits disappear quickly when they deal with bigger objects. Only one big reality survives. The many worlds theory works at tiny scales where gravity doesn't matter much. But many physicists doubt Penrose's idea of gravity. causing wave function collapse. Since the math isn't fully developed and the effects are hard to test, you'd have to create superposition in bigger and bigger objects to see how long it lasts. But today's technology can only manage that with small molecules. The objects needed to test this are too large for current experiments. More importantly, Penrose's theory would mean changing quantum mechanics by adding new ideas beyond the Schrödinger equation. Most physicists prefer sticking with standard quantum mechanics, which doesn't require such new concepts. The many worlds idea doesn't need any changes to the fundamental physics, only takes the math literally. However, Penrose still raises an important issue. We don't fully get how quantum gravity works yet, because general relativity and quantum mechanics don't fit together in their current state. To have a complete theory, we have to somehow combine them. Maybe once we do that, we'll find out gravity stops infinite branching. The universe might have a way to choose one possible outcome from many, or maybe gravity exists in superposition across different branches. It's possible there's no single space-time geometry, but instead different ones in different worlds. Equations from general relativity might describe multiple parallel spacetimes that evolve separately, not just one curved spacetime. Until we work out quantum gravity, we won't know which idea is right. David Deutsch created quantum computers not to solve everyday problems, but to show that the many worlds interpretation is real. His thinking was, if parallel universes are real, we should be able to tap into their computing power. A quantum computer with 300 qubits could handle calculations involving more states than there are atoms in the observable universe. Where does that power come from, if there's only one universe? A quantum bit, or qubit, can hold a value of 0 and 1 at the same time. 2 qubits can show 4 states at once, and 3 qubits can show 8 states. The number of states grows exponentially, doubling with each additional qubit. A 300-qubit computer can represent 2 to the power of 300 states at once, which is more than 10 to the power of 90. Classical computers handle one calculation at a time. To solve certain problems, they have to try each possible answer one by one. Quantum computers can deal with all possible answers at once because of superposition. When the computation is done, you measure it and get the result. The computer uses quantum parallelism to explore large sets of solutions, taking on problems that would take classical computers billions of years. Here's what's fascinating. While calculations are running, qubits are in a superposition of all states. The quantum computer is running calculations in parallel across all these states. In the many worlds view, each state is in a different branch of reality. The quantum computer creates many parallel universes, tackling different calculations in each, and combines the answers through quantum interference to give us the final result here. Deutsch claims this shows parallel worlds exist. How else could 300 qubits handle 2 to the power of 300 states at once? The computer must be using computing power from parallel universes, with each universe working on a piece of the calculation, then combining the results. Others see it differently. The Copenhagen interpretation says qubits don't have definite states until measured. The calculation takes place in an abstract quantum space that isn't exactly real. Pilot wave theory says there's just one actual state, guided by a hidden wave exploring all possibilities. Deutsch finds these alternatives unsatisfying. The many worlds interpretation is straightforward. The quantum computer runs parallel calculations in parallel worlds. Interference between worlds is what makes quantum computing more powerful than traditional computing. Without parallel worlds, quantum computers wouldn't have an edge. Yet quantum computers are still experimental. The biggest ones now have around 1,000 qubits, but can't maintain superposition long enough to solve interesting problems, Errors build up fast, and decoherence destroys the quantum state. Building practical quantum computers comes with huge engineering challenges, but progress hasn't stopped. Companies and research labs all over are racing to create quantum computers that can tackle real problems. Once they do, we'll have machines that use quantum parallelism to outperform any regular computer. According to Deutsch, this will be proof right on our desks that parallel universes exist. These computers will solve problems that a single universe alone cannot. Light travels at 300,000 kilometers per second, and nothing can move faster through space. This speed limit is like an invisible wall around us. Light from far-off galaxies took billions of years to get here, so we see them as they were long ago. The farther we look, the further back in time we see. But there's a limit to how far we can see. The universe is 13.8 billion years old. Light has only had 13.8 billion years to reach us. So, objects more than 13.8 billion light years away haven't sent their light to us yet. Their light is still on its way. This creates the cosmic horizon, or the edge of the observable universe. But the real distance to that horizon is more than 13.8 billion light years, because space itself is expanding. As light moves toward us, space stretches. So, the observable universe is about 93 billion light years across now. Anything beyond that can't be seen by us. It's not because something's blocking us, but because its light hasn't reached us yet. Now, think about bubble universes from eternal inflation. Each bubble is in a sea of superfast expanding space. The space between these bubbles grows faster than light can travel. It's not that things within space move faster than light, which can't happen. Instead, space itself expands so quickly that gaps between bubbles increase faster than light can cross them. This makes bubble universes unable to connect with each other. Light from one bubble never reaches another. Signals can't travel between them, and information can't cross that boundary. Each bubble is its own separate space and time. People in one bubble can't know about others, visit them, or communicate between them. The same goes for quantum many worlds. Different branches of a wave function separate from one another. They stop interfering and evolve on their own. These branches exist in a different kind of space, not our 3D space. But the separation is complete. You can't send messages to another branch. You can't travel there, or see what's happening in other worlds. This is why we can't visit parallel universes even if they're real. They aren't places we can reach by traveling a long distance. They're separate realities, kept apart by physics itself. The speed of light might keep bubble universes apart, and decoherence keeps quantum branches separated. Either way, these barriers seem unbreakable. Some scientists think about possible exceptions. Perhaps close-forming bubbles could connect through quantum tunneling. Maybe rare interference between quantum branches could happen with recoherence. Maybe wormholes or unusual space-time features could link them. But these ideas are very speculative. For now, if parallel universes are real, they'll stay separate from ours. But what if the cold spot shows they sometimes collide? Rory Mackenzie, a grad student at Durham University, spent several months looking over data from 2 big galaxy surveys. His goals seemed simple enough. Check if the Eridanus supervoid was real, and if it explained the strange cold spot in the cosmic microwave background. Back in 2015, some research claimed they found this void. Mackenzie wanted to double-check that with newer, more detailed data. He used info from the Anglo-Australian Telescope and the Gamma Survey, which mapped thousands of galaxies and measured their distances accurately. The method involved looking at light from galaxies since it has signatures from various chemical elements. As the universe expands, these signatures shift to longer wavelengths. This shift shows how far a galaxy is. By mapping out where galaxies are in a 3D space, astronomers can spot voids and clusters. The cold spot is about 5 degrees wide in the sky. If a huge void caused this cold spot using the integrated Sachs-Wolf effect, it would need to be massive. Some estimates said it might be 500 million to 1 billion light-years across. Something that big should easily show up in galaxy surveys. The area in front of the cold spot should have a lot fewer galaxies than nearby areas. Mackenzie ran his analysis by comparing the number of galaxies around the cold spot to those in other sky regions. The findings were unexpected. The region with the cold spot looked normal. The galaxy spread there was similar to other places, considering the measurement uncertainties. No huge void was seen in the data. He rechecked his calculations, used different statistical methods, increased the sample size, and looked at various distance ranges. Every test came back the same. There was no evidence supporting the supervoid hypothesis. The 2015 study claiming to find the void couldn't be confirmed with better data, and this caused issues. The cold spot is definitely real. Planck's satellite confirmed it, and multiple studies agreed on its properties. Something makes that part of the cosmic microwave background much colder than expected. If it's not a void, then what is it? Mackenzie and his advisor, Tom Shanks, sent their findings to the monthly notices of the Royal Astronomical Society in 2017. They admitted that it's troubling how standard cosmology struggles to explain such a large cold area. The chance of random fluctuations causing the cold spot is about 1 to 2%. Possible, but not likely, especially since no other similar cold spots have been found. The paper talked about exotic theories like cosmic textures, topological defects from early universe phase transitions, and bumps with other bubble universes during inflation. These ideas go beyond the standard cosmology model and are met with skepticism in the scientific community. But since conventional reasons are being ruled out, these exotic ideas are worth a look. Shanks said in a press release that if more research confirms no supervoid, then the idea of bubble collisions becomes a more reasonable explanation. This doesn't prove the cold spot is evidence of parallel universes, but it does move the idea from sci-fi fantasy to something scientists can test. This shift is significant. Science works by narrowing down options until only the truth is left, no matter how strange that truth might be. Laura Massini-Houghton at the University of North Carolina made a bold suggestion. The cold spot isn't due to random chance, and it isn't a supervoid. It's a scar from when our universe hit another one, before cosmic inflation pushed them apart. This collision happened 13.8 billion years ago, just after the Big Bang. Now, we see the results shown in the oldest light out there. This idea builds on eternal inflation theory. Tiny quantum fluctuations create bubble universes all the time. Most bubbles form too far apart to ever meet, but occasionally, two bubbles form close enough to bump into each other before inflation separates them. When these bubbles collide, they release energy at the border, sending a wave through both bubbles. From inside one bubble, this collision would look like a circular pattern in the cosmic microwave background. The pattern's size depends on when and where the collision happened in relation to us. Mathematical models predict certain temperature patterns. The cold spot fits these predictions fairly well, but not perfectly. Massini-Houghton takes it further. She thinks quantum entanglement links our universe to others created during the same inflationary period. Before inflation pushed the bubbles apart, they shared quantum states and became entangled. Even after they moved apart, the quantum connections stuck around. This idea is controversial. Most physicists think entanglement can't last between separate universe bubbles, because inflation expands space so fast it breaks any quantum links, and bubbles then can't affect each other. For entanglement, you'd have to verify connections through measurements, which you can't do if no signals can travel between these universes. Massini-Houghton argues that entanglement formed before inflation finished. The multiverse's quantum state includes bubble correlations as a permanent feature. We can't check these connections directly since we can't communicate with other bubbles, but they affect observable things. Like the temperature distribution in the cosmic microwave background, the cold spot might show quantum entanglement between universes. Her ideas face skepticism from many physicists. Critics say the cold spot might just be a statistical anomaly. Rare events happen, and weird features in cosmological data aren't proof of new physics. Big claims need big evidence. One odd cold spot doesn't prove a multiverse. Massini-Houghton admits there's uncertainty. She stresses that her idea can be tested. Future observations with higher resolution might show more about the cold spot structure. If it's from a collision, it should have certain geometric traits different from random changes. New cosmic microwave background experiments might give us data to decide between competing ideas. For now, her work is at the boundary of speculation and science. The cold spot could be unremarkable, or it might be our first look at another reality touching ours at the start of time. The evidence is unclear. The debate goes on. What's important is that this question has moved from philosophy to physics. Scientists are setting up experiments to see if other universes are real. We might find out in our lifetimes. Max Tegmark at MIT has a bold idea. If a mathematical structure is consistent and clearly defined, it exists as physical reality, not just as abstract equations. In the vast expanse of possible universes, every mathematical structure that can exist does exist. He calls this idea the mathematical universe hypothesis. It goes beyond the multiverse theories we've talked about before. Quantum. Many worlds theory says particles take different paths in different branches. Eternal inflation theory suggests different bubbles with different physical constants. But Tegmark's level 4 multiverse takes it further by proposing completely different mathematical structures. Imagine universes where time has 2 dimensions, or space has 17, instead of the usual 1 and 3. We're talking about universes with completely unimaginable mathematical laws. Why should all mathematical setups exist as realities? Tegmark thinks it's like a principle of fairness. If some math structures match up with real universes, why just some of them? What makes our universe's math special? Unless there's something external picking which math becomes real. The simplest explanation is that all consistent math creates reality. This might sound like a wild theory, but Tegmark points out that our universe seems to be completely driven by math. Every natural law can be written as an equation. Every detail about matter and energy is linked to math. Space and time form a mathematical shape. Quantum states exist in abstract mathematical spaces. The universe follows mathematical rules to develop. Maybe reality is just math. Maybe the world isn't just explained by math, but is math itself. We might be just patterns within a huge mathematical setup. Consciousness could come from complex mathematical processes. When we find mathematical truths through science, we are learning about our own universe. If that's true, then asking why our universe has its unique math is like asking why the number 7 is the way it is. 7 isn't chosen from other numbers. It just is. 7 is part of mathematical reality by necessity. Our universe might be one necessary structure in all possible ones. Critics say this can't be tested. How could we ever prove that universes with different math exist? We can't get out of our universe to check. The hypothesis doesn't make testable predictions. It turns into philosophy rather than science. Tegmark argues that it does make predictions. It says we should exist in a typical universe among those that can support life. Most mathematical structures probably can't create complexity. They'd be too simple or chaotic for life. We should expect to be in a universe that allows complexity. And indeed, our universe is surprisingly good for complex life without an obvious reason. The debate isn't settled, but the mathematical universe hypothesis is the most extreme multiverse idea. It's not just many universes with different traits, but infinite universes with every math structure possible. If Tegmark is right, reality is much larger and stranger than we can imagine. David Deutsch made a surprising claim. Parallel universes don't stay completely separate. Short moments of interference happen when quantum processes make previously similar universes different from one another. He says during the double-slit experiment, interaction between worlds briefly happens, creating interference patterns. Imagine an electron heading towards two slits. Before it hits the barrier, it exists in one universe. Then branching happens. In some, it goes towards slit A. In others, it goes towards slit B. The branches become separate. They are slightly different versions of reality, but they aren't completely separate yet. They are close enough that quantum interference can still happen between them. An electron going through slit A in one version interacts with an electron going through slit B in another version. This interaction creates an interference pattern. When the electron hits the detection screen, the versions completely separate. Interference ends. Each version has a screen with an electron hit in a specific spot. Inside any one version, you see one electron making one mark. But after many electrons, the pattern shows interference between versions. This pattern proves the electron interacted with something, even though no other electron was in your version. The interaction must have happened with the electron in other versions. Deutsch believes this explains why quantum mechanics works. Classical physics talks about one world. Quantum mechanics talks about the interference between many worlds. The wave function isn't just a math tool. It's a real thing that spans multiple realities. When we use the wave function to calculate, we're considering how worlds interact before they completely separate. Most physicists doubt this view. They accept the many worlds idea, but don't think interference between worlds is the right explanation for quantum experiments. The usual view is that interference happens within one version before any measurement. Only after measuring do versions split and become separate. No interaction between different versions is needed. Still, Deutsch's view has an interesting point. It naturally explains quantum computing. A quantum computer keeps a superposition across many computing paths. Those paths exist in different versions. The final result relies on interference between versions before measurement collapses the superposition. The computer uses temporary interference between parallel worlds to solve problems. Some new ideas go even further. They propose we might create situations where separated versions can come back together. This would require precise control over quantum systems, since any interaction with the environment causes decoherence and stops this from happening. But theoretically, quantum mechanics says we could get previously separated versions to rejoin if we could undo all the entanglements that divided them. If we could do this, we might achieve something amazing. Brief communication between parallel worlds, not travel or permanent contact. just fleeting moments where information passes between versions before they split again. This is way beyond what technology can do now, but the theoretical possibility is there. Somewhere in quantum configuration space, parallel versions of you might be dealing with the same problem you are. Your thoughts might subtly interact with theirs in ways too minor to notice, but the interference is real. How often does the universe branch? Every quantum interaction creates new worlds, and these interactions happen constantly everywhere. To figure out the overall branching rate, we'd need to understand how many quantum events occur throughout the entire cosmos. Start small. A single atom has electrons orbiting its nucleus. These electrons switch between energy levels. Each switch is a quantum event. Multiply by about 10 to the power of 80 atoms in the observable universe. Even if each atom only switches once per second, that's 10 to the power of 80 branching events every second. The real rate is much higher. Photons from stars constantly collide with atoms in interstellar gas. Cosmic rays hit planetary atmospheres. Rocks undergo radioactive decay. Neutrinos move through matter and sometimes interact with it. Each interaction causes entanglement and creates branches. Sean Carroll thinks the rate of branching around us is in the trillions of trillions per second. If you consider this across the whole observable universe, it's mind-boggling. Every galaxy has hundreds of billions of stars, and each star gives off quadrillions of photons every second. Whenever a photon hits matter, a new branch forms. The total number of branches becomes unimaginable. The universe might divide more times in 1 second than there are atoms in the observable cosmos. Does this make the number of branches infinite? Not necessarily. If the universe has limits in size and the number of particles, then branching is huge but still has a limit. Over 13.8 billion years, there could be a massive, yet countable, number of branches. Some cosmologists think this way, but others say the number must be infinite. If space is endless, then infinite quantum events happen all at once in the universe. Each second adds infinite new branches to the already infinite set. The multiverse becomes not just big, but infinitely so, in a way that goes beyond simple counting. The math of quantum mechanics doesn't say which scenario is correct. The wave function deals with probabilities for different outcomes, not counting branches or whether they're finite or infinite. This question remains unanswered in physics. Looking ahead, will branching ever stop? As long as quantum events happen, branching continues. But as the universe grows and cools, stars will burn out, galaxies will drift apart, and black holes will disappear through Hawking radiation. In the distant future, in trillions of years, there might be a time when quantum events are rare. Still, even in a nearly empty universe, there will be quantum fluctuations in the fields that fill space. Virtual particles will come and go. The vacuum itself undergoes quantum changes. As long as something exists, branching likely goes on. The multiverse might keep growing forever, adding new worlds without end. Every moment you exist, reality multiplies. Every thought you have leads to branches. Every decision makes parallel lives. The version of you reading this now is already just one among countless others that have emerged in the microseconds since you started reading. The branching doesn't stop. The multiplication never ends. Galaxies move away from each other. Space expands everywhere at once, but this expansion is speeding up. Gravity should slow the expansion as galaxies pull on each other. Instead, an unknown force pushes them apart more rapidly. This is known as dark energy. Dark energy makes up about 68% of all energy in the universe, but we don't know what it is. The main idea is that space itself has energy. Every tiny part of space contains a little energy, that causes expansion. This is the cosmological constant that Einstein introduced and later thought was his biggest mistake. The problem lies in the value. Quantum field theory predicts how much vacuum energy should exist based on virtual particles coming and going, but its estimate is about 10 to the power of 120 times more than what we observe. This is the most incorrect prediction ever in physics. Something is seriously wrong with our understanding. Some physicists say the multiverse might help explain this gap. If different universes have different vacuum energy values, then most would have energy far from what we see. In universes with a lot of positive vacuum energy, space grows so fast that matter can't gather into galaxies or stars. In universes with a lot of negative vacuum energy, space collapses too quickly for any structures to form. Only universes where vacuum energy is close to zero can have complexity. We live in one of these universes because life can't exist in the others. The multiverse and anthropic selection explain why the cosmological constant seems perfectly adjusted. It's not really fine-tuned. We just happen to be in a rare universe where the value supports life. Some scientists suggest something more extreme. Dark energy might be leaking from other universes. Imagine parallel worlds stacked around us in extra dimensions. If gravity can move through these, massive objects in nearby universes could affect our universe with their gravitational pull. From our point of view, this pull would look like an extra force either pushing things apart or pulling them together. The math is speculative. In brain cosmology models, our universe is a three-dimensional layer floating in a higher dimensional space with other layers nearby. Gravity works across all dimensions, connecting these brains. Dark energy might be gravity leaking over from neighboring brains. This theory can be tested. If dark energy comes from nearby brains, its strength might slightly change over time or across regions of space. Future studies with more sensitive tools might spot these changes. Standard vacuum energy should be completely uniform, but brain leakage would create patterns. So far, no patterns have been found. Current data suggests dark energy stays constant, but measurements keep getting better. Future surveys will track the universe's expansion more precisely than ever. If changes appear, we might find out dark energy is actually our first clue about other universes. The force pushing galaxies apart might be gravity from other worlds influencing ours. String theory calls for more dimensions beyond what we see. Older versions needed 9 spatial dimensions and 1 time dimension. These extra dimensions are thought to be so tiny we can't detect them. Each spot in our 3-dimensional space actually extends into 6 more tiny dimensions. However, some string theorists think these extra dimensions might be big, not small. We could exist on a 3-dimensional layer, or brain, within a larger space. This layer is our entire universe. We can't leave the brain or see the extra dimensions directly because all matter and radiation are stuck on the brain. Only gravity can escape into the larger space around all brains. This model suggests many brains float in this space, each a separate universe. The brains might be like sheets of paper stacked together or arranged differently. The space between brains could be tiny, even if the brains themselves are huge. What if brains collide? Neil Turok and Paul Steinhardt proposed the ekpyrotic model to explain that. They suggested our Big Bang was a collision between 2 brains. Before they hit, both were cold and empty. The collision released massive energy, heating both and filling them with radiation, creating what we know as the Big Bang. When the brains crash into each other, they bounce apart, move through space, cool down, and eventually collide again. This cycle keeps going forever. Every collision creates a new Big Bang. The universe keeps cycling through collisions, expansion, cooling, and contraction. In this model, time doesn't have a clear start or end. The idea of brain cosmology predicts specific patterns in the cosmic microwave background. These patterns should be slightly different from what we expect from standard inflation models. Also, gravitational waves from the Big Bang should look different. So far, there isn't clear evidence supporting or opposing the ekpyrotic model. The differences are tiny and would need more precise measurements to spot. Here's the important part about parallel universes. If we are on a brain, then other brains exist nearby in extra dimensions. Those other brains are separate universes with their own space, time, matter, and energy. The only connection is gravity, which seeps through the bulk. When brains collide, they leave marks. The collision releases energy, mostly where the brains touch. From our point of view on one brain, this makes a localized hot or cold spot in the cosmic microwave background. The size of this spot depends on the collision's geometry and where we are compared to the contact point. Some scientists think the cold spot might be evidence of a brain collision rather than a bubble collision. The math is a little different, but the effects look similar. Both predict circular oddities in the early universe's ancient light. Different parallel universe theories predict the same thing. We should see marks in the sky. Scientists need to be honest about what's uncertain. The cold spot has about a 1 to 2% chance of happening by random chance in the standard Big Bang model. That's like 1 in 50 or 1 in 100. Not impossible. Unlikely things do happen. Think about what a 1% chance means. If you flip a fair coin 7 times, there's about a 1% chance you'll get all heads. Surprising, sure. Does it mean the coin is rigged? Not really. Do the experiment enough times, and those 1% events will pop up regularly. With so many areas of the cosmic microwave background to check out, finding one odd spot shouldn't be a huge surprise. This is the conservative view most cosmologists have. The cold spot is odd. It should be looked into. But jumping to explanations about parallel universes is too quick when a simple statistical fluke could be the answer. Science needs us to try out all regular explanations before going to unusual ones. Tom Shanks from Durham University understands this. His team ruled out the supervoid idea, but that doesn't prove a bubble collision happened. He clearly said random chance is still an option. The cold spot might be just a big chance fluctuation that happened by accident. Maybe we got unlucky, or lucky, depending on how you see it. Still, the 1% chance bothers some researchers. Sure, unlikely things happen, but science moves forward by looking into anomalies. When what we see doesn't match what we expect, we learn. Maybe our predictions are off, or we've misunderstood something big. The cold spot makes us think hard about both. There's another thing to consider. The cold spot is unique. No other similar big cold regions show up in the cosmic microwave background. If 1% chance events happen randomly, we should see more than one cold spot. Instead, there's just one. This uniqueness is strange. The odds of seeing just one anomaly like this, rather than none or several, is even less than 1%. Some statisticians think we're asking the wrong question. We originally didn't decide to look for a cold spot in this exact position with specific traits, so our probability calculation is based on a guess. We searched the whole sky for anything out of the ordinary. Whenever you search for anomalies anywhere, the chances of finding something weird go way up. This is called the look elsewhere effect. If we could have noticed big hotspots, clusters of small cold areas, asymmetries, or strange geometric patterns, then finding one specific anomaly isn't such a surprise. The real chance could be more like 10% or 20% instead of 1%. Matthew Cleven, who studies bubble collisions, says we need more than just probability to answer this question. We need more data. Future experiments on the cosmic microwave background will map the sky in more detail. They might show details in the cold spot that distinguish random fluctuations from collision signs, or they could find other anomalies that make things clearer. Until then, that 1% probability hovers over the discussion, tempting speculation but also urging caution. Scientists are planning experiments to find direct evidence of parallel universes, pushing the limits of today's technology. Some experiments might be possible in a few decades, while others are theoretical ideas for future generations. One strategy focuses on the quantum many-worlds interpretation. If parallel worlds can briefly touch before splitting, we might see that clash in tightly controlled experiments. The goal is to create a big enough quantum system to hold information, keep it in superposition for as long as possible, and then see if interference patterns show properties of other worlds. Quantum computers might be good for these experiments. Current quantum computers can only stay coherent for microseconds. The quantum state falls apart before any interesting interference effects happen. But future quantum computers with thousands of stable qubits might stay coherent long enough for this to work. David Deutsch suggests that a highly advanced quantum computer could temporarily exist in multiple worlds before they split. Another approach looks for signs of bubble collisions in new cosmic surveys. The Simons Observatory and CMB-S4 project will map the cosmic microwave background with more detail than ever. If the cold spot is a sign of a collision, these tools should show predicted patterns in its structure. We might find many collision signs if we look close enough, or the data might rule out collisions altogether. Gravitational wave detectors give us another option. The Laser Interferometer Space Antenna, set to launch in the 2030s, will measure gravitational waves from the early universe. Bubble collisions should create specific gravitational wave patterns. These waves have traveled through space unchanged since the collision. Finding them would offer direct proof that our universe touched another one. Some scientists suggest we test if dark energy comes from the parallel dimensions. If extra dimensions exist, gravity should be different in strength on tiny scales. So far, experiments looking for changes from Newton's law at very small distances haven't found anything, but more sensitive tests are planned. Finding new forces at tiny scales would change physics and suggest nearby alternate realities. Testing the concept of eternal inflation is tough, since most bubble universes are out of reach. But we can check if inflation ever happened at all. The way density changes in the cosmic microwave background lines up well with what inflation theory predicts. Future tests might confirm this even more, or show new conflicts. If inflation is proven with certainty, eternal inflation seems more likely, since it's hard to start inflation without it going on forever in some areas. The boldest idea involves using quantum entanglement over long distances. If we could connect particles on Earth with those in a well-kept isolated system, and keep that system in a superposition long enough, we might see links that only fit within a many-worlds theory. This would need technology we don't have yet. If successful, it would show quantum effects can be seen at larger scales. These experiments might not succeed. Parallel universes might be real but still undetectable, or the tests could fail, not because other worlds aren't real, but for technical reasons. Still, trying is important. For the first time, we have real ideas on how to test if other realities are out there. If every choice you make creates other paths where you chose differently, does free will exist? In some paths, you chose to read this. In others, you stopped earlier, or never started. All these versions are real, each feeling like they made free choices. But if all possible outcomes exist, then your choices may seem meaningless. You can't cause or stop anything entirely. Everything possible happens somewhere. However, this misinterprets choice in the many worlds view. When you make a choice, you decide which path to follow. You can't stop other paths from existing, but you can choose which one includes you. This is real free will for your personal experience. Imagine it from inside one path. You face a decision, think it over, weigh options, and decide. Your choice changes your future. This path's version of you lives out the results of that choice. Other paths exist, but you only know this one. Your choices here matter and have real effects for you. The debate between determinism and free will is an old one. Many worlds doesn't so much solve it as it offers a new angle. In a universe with one storyline, your choices might just follow from previous causes, going back to the Big Bang. Many worlds suggests your choices are set, but they decide which path you take, rather than the overall outcome. Some think this keeps moral responsibility intact. If your choices shape your reality, you're accountable for them. Other versions making different choices don't let you off the hook for your choices' outcomes. Each version is responsible for the path they choose. Others argue that many worlds remove moral importance. If everything possible happens somewhere, then nothing is truly banned or needed. Bad things happen in some paths, heroic deeds in others. The multiverse includes all moral possibilities. Why focus on just our own path when all paths exist equally? It's because you only experience your own path. You can't see or interact with the other paths. Your choices are the ones that matter, since you'll deal with their results. Moral philosophy is about the reality you live, not all possible realities. There's a practical side too. Even if every outcome happens somewhere, some paths are more likely than others. Your choices can affect which paths are more likely. Making good decisions could make good outcomes more common, giving moral choices real importance even if many worlds exist. The most important point is that the many worlds theory doesn't tell you what to do, just what is. Whether you have free will depends on its definition. If free will means controlling all outcomes everywhere, then no. If it means shaping your own path with your choices, then yes. This question is still as open as ever. The European Space Agency is rolling out Euclid, a space telescope to chart billions of galaxies. It launched in 2023, and data collection is underway. We'll see results in the late 2020s and early 2030s. Euclid aims to give us a clearer view of the universe's structure. If oddities like the cold spot have patterns we can't see right now, Euclid might catch them. NASA and other global teams are working on the Nancy Grace Roman Space Telescope, set to launch mid-2020s. Roman will run infrared surveys and measure distances to millions of galaxies, showing dark energy's effect over time. If dark energy changes in ways suggesting other universes or shifting gravity, Roman could find it. Ground-based telescopes are advancing too. The Vera Rubin Observatory in Chile is starting up soon. Its telescope will photograph the entire visible sky every few nights. Over a decade, it will create the most detailed map of the universe yet. Any peculiarities, be they gravitational oddities or unexpected patterns, will appear in this data. CMBS-4, the next-gen cosmic microwave background experiment, is set for the late 2020s. It will use detectors in Antarctica and Chile to measure Big Bang light with incredible precision. The temperature maps will be detailed enough to show structures we can't currently see. If bubble collisions happened, CMBS-4 will confirm or deny them once and for all. The Laser Interferometer Space Antenna will launch in the 2030s. 3 spacecraft will work together, spaced millions of kilometers apart, to catch gravitational waves from the early universe. These waves hold clues about events right after the Big Bang. If there are signs of colliding universes or bubble universes, they should show up in the gravitational wave data. Quantum tech is moving fast. Companies and labs are building stronger quantum computers. Current ones have about 1,000 qubits. The next ones might hit 10,000 qubits or more. Eventually, these computers may be able to test the many worlds theory directly, possibly showing processes that only make sense if parallel paths exist. Particle physics experiments keep searching for extra dimensions too. The Large Hadron Collider hasn't found evidence yet, but upcoming upgrades could change this. With higher energy crashes, some particles might be created that can slip into extra dimensions, showing up as missing energy in detectors. Discovering these particles would support the idea of brain cosmology and suggest parallel worlds nearby. These experiments will provide results within the next 20 years. We're moving into a time when theories about parallel universes are becoming testable science. The data will either support the idea of a multiverse or severely limit it, but either way, we'll learn more than we know now. Whether other realities exist might be answered during your lifetime. The idea of a cosmic bruise could be explained. Quantum computers might remember being in multiple states. Gravitational wave detectors might pick up signs from another universe. Or we might find out the multiverse is just an illusion, and our universe is all there is. Maybe the strange details and oddities of quantum physics have simpler explanations we've yet to discover. In 20 years, we'll probably have an answer. The experiments are starting, telescopes are being built, and the measurements are planned. Answers are on the way.